Okay guys, so we've made it to section 5-3, which is going to begin using the fundamental theorem of calculus. Now we won't actually prove the entire theorem until 5-4, but we have we've got the concept down that the area under the curve of a function, so this is our function f of x, between a and b. We learned in the video in class that that area, which you could call it a for area of x, is a function of x depending on where we choose to place the x, and this turns out to be the antiderivative of this curve with respect to x. So, and we will again we will look at this in much more detail in section 5-4, but we can begin using this idea to evaluate definite integrals. So we have basically made the connection between integrating something, which is finding the area under the curve, and antiderivatives, which that area under the curve ends up being. It's a huge idea in calculus, which is why it's referred to as the fundamental theorem of calculus. The part of it that we're going to be using today is part 2. So we're kind of cheating, okay? We're cheating a little bit because we haven't proved the theorem yet. We haven't looked at part 1, and we're already going to go ahead and start using part 2, and that's because part 2 is really the part that we use when we actually solve problems and those kinds of things. So if it's still shaky, if the concept is still shaky to you, don't feel bad, because in 5-4 we're going to come back and we're going to really solidify this theorem. We're going to prove part 1 and then look again in more detail at part 2. For right now, we just want to understand the fact that the area under a curve and the antiderivative of f are one and the same. So a of x is the area under the curve, and that's what this integral means, because it's the sum of all the rectangles, base times height. So these are basically area under the curve is equal to the antiderivative of f. So you could say that dA dx is equal to f of x. So if I took the derivative of this function with respect to x, I would have f of x. So if I take the antiderivative of f, if I go backwards, I would have a. So this is the notation that was used in the video we watched by Professor Berger. In our book, it kind of goes a little something like this. So we're basically told that if we want to find the area under a curve between 2 points A and B, if we want to find this area under the curve, we just need to find the antiderivative of f, and for that they use capital F. Evaluate that at B, and then evaluate it at A and subtract them. This is basically part 2 of the fundamental theorem of calculus, where the derivative of capital F is equal to lowercase f. In other words, if I take the derivative of this function, I would be given this function. So if I went backwards, if I found the antiderivative of little f, I would have capital F. So basically, we're going to be finding antiderivatives, plugging in these endpoints, and taking the difference. And so, again, you can think of capital F of x as the function of the area under the curve of f of x as a function of x. So you could think of f of b as like all of the area under this curve from negative infinity till b, so to speak. You could think of it that way. Subtract away all the area under the curve of f from negative infinity to a. That's how you can think of these two values. So f of b is all of the area under the curve from negative infinity to b. Capital F of A is all the area under the curve from negative infinity to A. And if I subtract all of this by all of that, I would just have the area between A and B. So that's just sort of the general idea of the fundamental theorem of calculus part 2. And it turns out it's not too hard to do. And so we're going to basically use this right here to evaluate definite integrals. This is when no known formula for area exists, because think back to 5.2, we were able to evaluate these integrals using area. That's still totally fine as long as a valid area formula exists. If not, then we're going to start using antiderivatives. Okay, so for example 1, I'm giving here a definite integral, and again, let me just specify because I don't know if I have yet. A definite integral is when we are given a lower bound for integration and an upper bound. In other words, we're given endpoints. In this case, the lower bound would be 0, and the upper bound, right there, would be 2. Since I'm giving those values, that's what makes it definite. It's like an actual number. It's an area under the curve. Okay, so in this scenario, my equation is the graph of a line. So I have options. I could either use the area for a triangle, or I can use an antiderivative. In fact, I think I'm going to go ahead and show you both. So this is if I were just going to use a given, a known area formula. This is kind of a little review of 5.2. I would sketch the curve between 0 and 2. And so I notice it has a y-intercept of -3. And it has a slope of 2. And I'm finding the area under this curve because, again, that's what the integral means, is the area between the curve and the x-axis. So I would basically use a formula for this triangle, find that area, and then I would use a formula for this triangle, find that area. This, of course, would be negative area. This up here would be positive area. I would find them, subtract them, and get my answer. So this would be 1/2 base times height. The height is 3, and the base depends on that intercept right there. I have to figure out what that is really quick. So I'm just going to figure out what the x-intercept for that line is. So I'm going to set, so this line is, I'm going to set the function basically equal to 0 because the function equals 0 at that x value, or t value in this case. So I get 2t equals 3 and then t equals 3/2. So it looks like it intersects the x-axis halfway between 1 and 2. And so that would also be this base of the triangle would be 1.5, 1.5. And that's going to be negative area. So I'm going to have 1/2 base, which was 3/2, times height, which was 3. So that ends up being 9/4, and it's negative. So that is an area of -9/4. And then this positive area right here, again, I'm going to do base times height. And so this would have to be 1/2, or 0.5. That height would be 1. And so for this triangle right here, it'd be 1/2 the base, which is 1/2, times the height, which is 1, so it's 1/4. So I add those two together, and I get -8/4, or -2. So that method totally works. That's the 5.1 method. Because that was a straight line, so it formed triangles, so there was a known formula for that, totally fine. But let's practice doing the antiderivative because it's easy to do with lines, and so we can learn that method as well. According to the Fundamental Theorem of Calculus Part 2, I need to find the antiderivative of whatever function is in the integral, and then evaluate that antiderivative at the given numbers, the given lower bound and upper bound. So I have to think backwards. I have to ask myself, what must the original function have been in order for its derivative to be 2t minus 3? We have to think backwards. Well, we know that derivatives go down in powers. So if we're going to go backwards, it must go up a power. And also, this number in front, the 2, must have been the original exponent, because when we take a derivative, we bring the exponent and make it a coefficient. So this coefficient must have been the exponent. So right away, I can see that the first part of the original function, the antiderivative, must have been t squared. And I can just sort of check myself. If I took the derivative of that, I'd have to bring the 2 in front. So I'd have 2t, and then I'd have to drop that power down by 1. So I have 2t to the first, which is exactly what I have here, so I know I have the first part right. And then I would have to find the antiderivative of a constant. Well, that means that basically this exponent is 0. You could kind of think of this as like t to the 0. So the original exponent must have been a 1. And so I believe the original would have been negative 3t to the first power. I can check that because if I took the derivative of this, I would bring the 2 in front, drop that power down by 1, so I'd have 2t minus 3. And that's exactly what was inside the integral, so this must be the antiderivative. But then I have to evaluate this at 2, so I'd have to find capital F of 2, which is the antiderivative evaluated at 2. So that gives me 4 minus 6 is negative 2. And then I'd have to evaluate it at 0, which gives me 0 squared minus 3 times 0 is 0. And then I would have to do the difference between f evaluated at the upper bound minus f evaluated at the lower bound, which would be negative 2 minus 0, which would be negative 2. So you can see that whether you use an area formula or antiderivative, you will get the exact same answer. So it turns out that the area under a curve and the antiderivative are one and the same. In part 1 of these notes for 5.3, I just wanted to clarify one thing that I wasn't sure if it came across clear in the first part, and that is, in the video we watched in class with Professor Berger, he called the area under a curve A of x. And that was basically the area under the curve of x as a function of x, which turns out to be the antiderivative of that curve. And then in our book, instead of referring to that area as capital A of x, they refer to it as capital F of x. So that's the connection that I wanted to make. So if you could put a note to self for the first part of these notes, that in our book, when they use capital F, that's the same thing as in the video we saw in class when they used capital A. It's basically meant to refer to the area under the curve of lowercase f, which is also equivalent to the antiderivative of lowercase f. There's 7 rules of definite integrals. I know I only have 6 here because there's a 7th on the next page. This is going to look familiar and remind you of the rules of differentiation because they're very, very similar. The first one is called the order of integration, and that is that you basically, when you're writing a definite integral, it should always have the lower bound at the bottom. This is very important that we get the notation, and then the upper bound should go at the top. So the smaller number should be at the bottom, and the bigger number should be at the top. If that gets switched, it will change the sign of the area. So if you put the larger number on the bottom and the smaller one on the top, you could still find that integral, but then you would have to change the sign if you're trying to find this area between a and b. So when you change the order of the limits of integration, the sign of the area changes. So that was the first sort of rule. Okay, then if you have a 0 area, if you're finding the area between a and a, so if we're finding the area between a and a, so in other words, there's no area because there's no change in x, that area would be 0. Okay. Then for number 3, we have the constant multiple rule, which is going to be exactly like the constant multiple rule for derivatives. So let's say you're trying to find the area between a and b of a constant k. So k is a constant, it is not a variable, times the function and then dx. That's the same thing as just multiplying the constant to the area under the curve. So you can just sort of pull the constant out, or think of it as find the area under f, or find the antiderivative of f evaluated here, and then multiply by the constant. Okay, and then we have the sum and difference rule, which again, this should also look extremely familiar. And it's a good one. You're going to like it. No fancy rules or anything. Let's say we're trying to find the area under the curve of f of x plus or minus g of x. I'm going to kind of squeeze them together as one property. So you can either have a sum of two functions or a difference of two functions, and the nice thing is you can take the integrals separately. So you could do the area under f first, and then add or subtract that to the area under g. And it's just a very nice thing. It helps simplify the process when we have to take the antiderivative of a complicated function. If it's split up with plus and minus, we're good to go. We can just take the antiderivative separately, or the integral separately, and then add or subtract the final areas. Okay, and then this next property is called additivity. It's kind of a fancy name for a really basic idea. But pretty much how it works is, let's say you're trying to find the area between a and b of a function. Well, and let's say it's kind of hard to do because it's split up by a point of discontinuity, or maybe it crosses the x-axis at a certain point. So sometimes we need to split it up, and that's fine. So let's say c is some x value between a and b. You could think of this as the area between a and c under f plus the area between c and b under f. It's like, in other words, like if I look back at this picture up here, let's say I had some c and it was like right here. I could basically find the area under f between a and c, if that were easy to do, and then find the area under f between c and b, and add those two areas together, and I would have the area under f between a and b. So that's just kind of allows us to split up the limits of integration. Okay, and then the next one we have is called the max-min inequality. And so that basically says, like, let's say you have a maximum value of a function. So let's call that max f, and that's the maximum value of f. Then let's say you have a minimum value of a function. We'll call it min f, and it's just like the lowest point on the curve. Well, you could say that, and I'm running out of room, of course, but basically you could say, how about we'll use this space over here, that the minimum value of f times b minus a is less than or equal to the integral between a and b, f of x dx, is less than or equal to the maximum value of f times b minus a. So you're probably wondering what the heck that's all about. So because I ran out of room, I'm going to go ahead and use like a piece of scratch paper. So you can kind of feel free to go ahead and do the same. But basically it kind of works like this. So this max f and min f are like different heights. So you can kind of put in parentheses height and height. And this b minus a, well, that's a base. It's a change in x. So let's go ahead and I'm going to kind of make a real nice, obvious sort of max min. So here's a, here's b. Let's say we have, let's just make it a straight line. That'll make it real obvious. So here's my, on this interval. So we have to sort of, when we have interval, we have to ignore everything else. On the interval from a to b, so I'm going to block this out of my mind, and I'm going to block that out of my mind. This is clearly the lowest value out of all f values. So we'll call that min f. And this is clearly the highest value out of all the other f values. We'll call that maximum f. Okay, so b minus a then is this length right here. It's the base because it's the difference between b and a. So if I took this minimum value of f, min f, and multiplied it to the base, I basically would have found the area of this teeny tiny rectangle down here, because it's the lowest value of f times the base. So that right there, this shaded in red, so I'm going to put red area, is the min f times b minus a. Okay, now if I were to find this right here, the maximum value of f times b minus a, well, that would be up here. So here's the maximum value of f, it's way up here, times b minus a, that would be this rectangle, the one colored in pencil. That would be the maximum value of f, which is this height, times this base. B minus a creates that rectangle. So the shaded one in pencil is max f times b minus a. Okay, now, the integral between a to b, f of x dx, is exactly the area under the curve, but above the x-axis between a and b. So the area that I now have colored in blue, that area is the integral from a to b of f of x dx. So you can see clearly the red area is the smallest. It's the least of all the areas. The pencil area is the most. It's the greatest of all the areas. And the actual area under the curve, the integral, is somewhere in between the red and the pencil, or somewhere in between min f times b minus a and max f times b minus a. And that's what this whole sort of inequality is all about. So this area would be the least amount of area. This would be the actual area, and this would be the most area. And that inequality will come in handy when we're trying to sort of approximate and figure out what this would be. We could find these two rectangles, and we know that we have to be somewhere in between those. So that's where this would come in handy. So the last property of the definite integrals is called domination. And it's basically saying that, let's say you have two functions, f of x and g of x, and f of x is greater than or equal to g of x, meaning that the values of this function are always higher up than the values of this function. These values are always greater than these values. If that is true, on some interval from a to b, that would imply, so this double-lined arrow means implies, that implies that the area under f from a to b, of course, is going to be more area than that under g. Because these heights, these y values are always higher than these, so the area under them will be more than the area under g. And kind of a special case of that, or scenario that has to do with this domination thing, is let's say you knew that for on some interval a to b, let's say that, so this is sort of a special case. Let's say that f of x was greater than or equal to 0 on some interval. In other words, it's positive. It's above the x-axis or on the x-axis for some interval. That implies that the area is positive. That implies that the area under that curve, it would be positive area because the function itself is above the x-axis. Kind of a special case or special application of this domination property. Okay, so basically we're going to use all of those properties, 1 through 6 and then also number 7, to evaluate different integrals and things like that. So if you look at the way example 2 is set up, it might kind of look familiar to you. AP Test loves these kind of problems where they don't tell you what f of x is and what h of x is. They don't tell you what they are. They just let you know that they're continuous functions. Okay, these properties that I gave you are only true for continuous functions. So if you could go back to your first page real quick and kind of make a note to self, rules for definite integrals, and we'll say basically for all of these, let f of x be a continuous function. Sorry, sometimes I leave out the details because I forget. But it's important that we understand that this is true when the function that we're talking about is nice, smooth, and connected. Okay, so back to the problem at hand. So I know that f and h are continuous functions, which means I can use all the properties available to me. I know that the area under f between 1 and 9 is -1. I know the area under f between 7 and 9 is 5. I also know that the area under h between 7 and 9 is 4. So I can use those three pieces of information to find these areas. Very similar, we have very similar problems like this when we did derivatives. So we don't know the function, we don't need to know the function, all we need to know are areas under the functions. So for this one right here, I already know what the integral from 1 to 9 of f of x dx is. I just have to figure out what the integral from 1 to 9 of negative 2 times f of x dx is. So I'm going to use the constant multiple rule, which allows me to basically just pull the negative 2 out of the integral and think of it as something separate. And I know the value of this integral because it was given to me is negative 1. So I can think of this as negative 2 times negative 1. And so the answer is 2. These are meant to be super easy as long as you know your rules of integrals. Okay, next part is find the area under f between 1 and 7. Well, I was not given that, but I was given the area between 1 and 9, and then the area between 7 and 9. So if I took the area between 1 and 9, I could think of that as the area between 1 and 7 plus the area between 7 and 9. And that's based on the additivity property. So this one I'm using additivity property. So I first would sum up the area between 1 and 7, figure out what that is. Sum up the area between 7 and 9, and then if I added all that area together, I'd have the area between 1 and 9. Well, I know that between 1 and 9 is negative 1. So I could say, okay, negative 1 equals this, which I don't know, plus this area, which I was given, was 5. So if I subtract 5 from both sides, I'd have negative 6 equals the area between 1 and 7 of f of x dx. And so that would be my answer for B. So it's the area from 1 to 9 minus the area from 7 to 9. Okay. Then for part C, I basically would use the a couple different properties. One, I noticed that the limits are out of order. So I would use the order of integration property to switch them back. And I also noticed that I have a difference, so I would use the difference property also. And so I basically first would switch the signs. So this is really negative integral from 7 to 9, h of x minus f of x dx. And then, move this down here, and then I basically would split it up. So I'd have negative integral from 7 to 9 of h of x minus integral from 7 to 9 of f of x. And the nice thing is these two values were given. The 7 to 9 h of x is over here is 4. The 7 to 9 f of x right here is 5. So I'd have negative 4 minus 5. So it'd be negative, negative 1, which is positive 1. So part C would be positive 1. Sorry, I kind of ran out of room there. Hopefully you were able to follow every step. For example 3, I'm going to use the max-min inequality property. Because in a sense, they're kind of hinting at that's what they want me to do. They want me to show that this value lies between two things. Lies between sort of is the key word there. They basically want me to set this up where I'd have like 2 rad 2 is less than or equal to this is less than or equal to this. That's basically what they want me to do. Show that this lies between these two areas. So if I could use the minimum value and the maximum value along this interval, I'm good to go. So maybe we'll go ahead and sketch a graph of this function. Notice it's a radical function, which is what I like to refer to as the, quote, eyebrow function. So if I sketched a graph of it, oh, and I notice it's going to have to go all the way over to negative 8, because that's the value of x that would make the inside 0. So I'll leave myself some room to do that. And I am only looking at this function between 0 and 1, but it helps to have the whole function in mind. So I know that it would have a point at negative 8, 0. And if I plugged in -7 plus 8 is 1, and the square root of 1 is 1, so I'd have a point there. If I plugged in -4 for x, I'd have the square root of 4, which is 2. And it kind of would look like that. And I'm looking at the area under the curve between 0 and 1. So I'm looking at that area. And I want to show that it is between 2, rad 2, and 3. So what I will do is find the minimum value of the function and then the maximum value of the function. And this is kind of a nice one because this function is strictly increasing, meaning the bigger x gets, the bigger the value of the square root gets. Strictly increasing. Okay, so in other words, the larger the number inside, the larger the outside square root will be, which tells me that the minimum value will occur when x is 0 along this interval. So the minimum value is going to be right there, and the maximum value will occur when x is 1, because I'm only looking at the interval between 0 and 1, and the function is consistently increasing. So the lowest point would be the left endpoint, and the highest point would be the right endpoint. So the minimum value of f would be the square root of 8, or 0 plus 8, which is the square root of 8, which, coincidence, is 2 rad 2. The maximum value of f would be the square root of 1 plus 8, which is the square root of 9, which is 3. What a coinkydink. So I basically can use the max-min inequality, which says the minimum value of f is always going to be less than or equal to the area under f, and that'll be less than or equal to the maximum value of f. Oh wait, sorry, I forgot to write times b minus a. So the minimum value of f times b minus a is always going to be less than or equal to the area under f, and that's always going to be less than or equal to the maximum value of f times b minus a. So I need to figure out what b minus a is. Well, b is 1, and a is 0. So b minus a, which is equal to 1 minus 0, is 1. So I can basically say then that the minimum value of f, which is 2 rad 2, times 1, is going to be less than or equal to the integral from 0 to 1 of square root of x plus 8 dx. And that's less than or equal to the maximum value of f, which was 3, times b minus a, which is 1. And so I basically have effectively shown that the area under this curve lies between 2 rad 2 and 3. So kind of let the wording of the problem guide you as to which property you would use or whatever. Okay, so moving on to average or mean value of a function, and it kind of has a lot to do with this whole max-min thing. Basically, if you have the area under a curve, so again, I just use the same kind of flowy, pretty, smooth, continuous curve, and it's between A and B. So if you have that right there, that area, all of that lovely, lovely area, I'll use red to make it stand out. Nice area is denoted by this integral. So if I took that area, which basically, remember this stood for an infinite sum. It's an infinite sum of infinitely many rectangles, and the rectangle is indicated by the base, which is the change in x, times the height, which was the f values. So this kind of was base times height, base times height, base times height, base times height, an infinite number of times and adding it all together. So that's how we get that area. So if I took that area, all of that lovely red stuff, all of that area under the curve of f, which is denoted by this integral, and divided it by the base, which is b minus a, I would be left with the average height, or the average value of f. Now remember, f of x is what determines all the heights of the rectangles. This right here is all the heights times b minus a. So it's like height times b minus a, 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 infinitely many times. So it's all the different heights times b minus a. Divide that by b minus a, divide it by the base, you would be left with the average height. Okay, because this here is base times height. Divide out the base, you get height. And you get the average height, or the average value of f. Now the way the book writes this is they have it as 1 over b minus a, which is the same thing as dividing by b minus a, times the interval from a to b of f of x dx, and that's just equal to the average value of f. And this is what we use to find average values of functions. To find maximum values of functions, we use derivatives. To find rates of functions, we use derivatives. But if we want to find average values of functions, we use integrals. We use the antiderivative. We find it, and then we divide by the base. And that gives us the average. This is such an important thing to remember. This is the kind of property or formula that the AP test likes to sneak in. They like to sneak in that word average value. So every time we're doing an average, we're always going to divide by a change in x. So it's basically the integral divided by the change in x. And so I'm going to go ahead and do this example 3 right here. And you'll see it's really easy. So if I can remember what this means, the average value, and just go straight to the formula, it's really easy to do. So in this scenario, a would be 0, and 3 would be b. So a is 0, b is 3. So I'm going to do 1 over 3 minus 0, b minus a, times the integral from 0 to 3, a to b, of f of x, which is the negative x squared over 2 dx. So that's basically 1/3 times the integral from 0 to 3, negative x squared over 2 dx. And for this, I'm going to have to find the antiderivative of a negative x squared over 2. So we have to think backwards. Well, I know the power in front is a 2. So the original power must have been a 3. It must have been a 3 because I had to go down by 1. So let's go ahead and find a function and see if it works. So I know I had to have, and I have a negative there, so the original must have been negative. Negative x to the 3rd. So if I were to find f prime of x right now, I would have negative 3x squared. So close, but not quite. There's a 1/2 in there. So I need to figure out what times 3 would equal 1/2. So 3 times what number would equal 1/2? And that number would have to be, some people will write it as 3x. 3x equals 1/2. X would have to be 1/2 times 3, or 3/2. So let's try that. Let me go ahead and put 3/2 in front. Or no, what did I do? Oh, divided by 3, my bad. Divide by 3. So I need 1/2 times 1/3, so I need 1/6. Okay, just kidding. So let's try negative 1/6. Now let's find the derivative. If I multiplied 1/6 by 3, that would get me the 1/2, and I'd have negative 1/2 x squared. So there we go. Here is my antiderivative, is negative 1/6 x to the 3rd, and I have to evaluate that at 3, evaluate that at 0, and then subtract. So let me get all this scratch work out of the way here. So then I'm going to do, so this all is equal to 1/3 times f of 3, which is negative 1/6 times 3 to the 3rd, minus f of a, which is negative 1/6 times 0 to the 3rd. So that's 1/3 times negative 1/6 times 27 plus 0. So then that all turns out to be negative 1/18 times 27. And that ends up equaling, let's see, divide by 9, negative 3/2. So I began with the formula, plugged in A and B, simplified, did some scratch work to find the antiderivative, plugged B into the antiderivative, plugged A into the antiderivative, subtracted, and multiplied by the 1 over B minus A, and got negative 3/2. Okay, last but not least, we're going to go ahead and look at the mean value theorem for definite integrals. And that basically states this. It's also on page 272 in your textbook, which you can look at for further explanation. But it just basically says if f is continuous, like smooth and connected along an interval from A to B, that implies that there exists some x value c. Such that the value of f at c would be that average value. It's exactly like mean value theorem for derivatives, which says that there is some c where the derivative and the slope of the secant line are the same. The slope of the tangent equals slope of the secant. Instantaneous equals the average. This is similar, except it's not the derivatives, it's the actual function itself. The function at some point will equal its average value if it's continuous. That's all that this is saying. And I will show a picture of this in class. I'll explain this a little bit more in class. It's also on page 272 of your book.